Okay, so just a reminder, assignment 5, which is a quiz, is due tonight. Okay. So we will continue with, yes, so you're all supposed to hear anything I'm talking. So if you cannot hear, please check your microphone is working. Okay, so somebody says they cannot hear. Please check your microphone. Okay, so now we are going to look at the flow control and congestion control problem with TCP.
Dr. Meg,
Yes,
can we find out our grade with the last few assignments, or are they not graded yet?
they
With
are not
those
yet
two.
graded, so I'm going to grade it this weekend.
Okay.
Yeah. Alright, so flow control is the mechanism of adjusting the sending rate according to the resources available at the destination. So basically, we don't want the source to keep sending at a rate that the receiver cannot accommodate. Okay, so the receiver will have only some limited buffer space. So if the sender keeps sending, and you also should remember that there's an application running at the receiver side as well as the sending side. So the sending side application is sending the data to the receiving side application. So the application needs to be able to read the bytes that are received at the transport layer, which are buffered at the receiver side. So if the buffer space gets full and the application running at the receiving side is still have not read the data, then the transport layer protocol running at the receiver side cannot anymore accept the data. So it will run out of buffer space. So at that time, the sender should not send any more data, because any further data sent will simply be dropped because they cannot be stored unless the application reads the data from the buffer space and clears some buffer space. So the available buffer space at the receiver side is what is called the advertised window, and the receiver should advertise that available window space every now and then, so that the sender knows how much to send without overflowing the receiver. So this is the flow control problem we are going to see. Now, typically, you could think that in order to keep things simple, you could go through what is called a stop and go approach, where the sender sends just one packet, called one data packet of one MSS. You all know what a maximum segment size means by now. So the sender can send one MSS amount of data and just wait for an acknowledgement to come before sending the next data packet. Now I have shown an example here where the source will send say 1000 bytes of data in a channel of bandwidth 8000 bytes per second. So that means on that network attached to the source, you could send 8000 bytes per second, and the source sends 1000 bytes of data. Now it takes some time for the data packet to propagate to the destination, and once the destination receives it, it will send an acknowledgement. Now the sender, if the source decides to send only one data packet at a time and wait for an acknowledgement before sending the next data packet, then the source would have to wait for that amount of time for the acknowledgement to come back, and we will call that as a round trip time. So the round trip time is basically twice the propagation delay. So after you insert the data bytes onto the channel, the delay that is taken for the bytes to propagate to the destination and for the acknowledgement to come back is basically the propagation delay. So propagation delay in one direction plus propagation delay in another direction, so that is 2 times the propagation delay is the round trip time. So if the source waits for the round trip time, it would have just sent 1000 bytes of data in 2 seconds. So somebody has the microphone on, so it's echoing. Okay. So the stop and go approach So in 2 seconds of round trip time, you could really send 8000 bytes times 2 seconds, which is 16,000 bytes of data. But you're really sending only 1000 bytes instead of 16,000 bytes. So the efficiency of channel utilization is simply 1 over 16, which is less than 10%. So this is what we want to kind of increase or maximize. So what we want to do is, we don't want to go too pessimistic, in the sense that not just send one data packet and wait for an acknowledgement. We want to be able to send several. So how much? So we call it as a sliding window, and how much we send per window is what we are going to estimate. Now ideally, if the receiver's advertised window allows, we want to send as much as possible. And what is that as much as possible? From the source point of view, it is the RTT times bandwidth product. So the RTT times bandwidth product captures or gives you the estimate of how much we could send from the source side by exploiting all the bandwidth available at the source network. So like in this case, you could send 8000 bytes of data per second from the source network, and if the round trip time to wait for the acknowledgement to come back is 2 seconds, so in 2 seconds we could send 8000 times 2, which is 16,000 bytes. And let us say if the data packet size is 1000 bytes, so 16,000 divided by 1000, which is 16. So one window is basically 16 data packets. You could send 16 packets before you could wait for an acknowledgement. And after you get an acknowledgement, you send some more data packets. Now by the receiver side, all the 16 could come in order, some could come out of order. So the destination will typically acknowledge for the last byte received in order. So it may not acknowledge for every data packet, it would acknowledge for the last byte that was received in order, and based on this the source should be able to track how much more it could send. So those are the details you are going to see. So I explained all these things in this slide, so you can go through it. So let us now use an example to kind of see a motivation or how to do this flow control at the byte level. So there are 4 variables that we keep track of, 2 at each side, and some more, there are 2 more, so totally you can say 6 variables, but 4 of them are really important. So let us say the source has sent some bytes, and we have the byte numbers indicated here, the sequence numbers of the bytes. So 2000 is the sequence number of the last byte for which the source has received the acknowledgement from the destination or receiver. So we call sender receiver or source destination, they mean the same. Now the source has sent some more bytes of data, and the last byte, the sequence number of the last byte that was sent is 2600. So that's what this number means. And the application at the sending side has returned to this buffer at the transport layer protocol at the sending side up to 3000 bytes of data. So there are still 400 bytes of data. 3000 minus 2600 is 400 bytes of data that are yet to be sent from the sender point of view. Now from the receiver's point of view, in keeping in sync with these numbers that are shown here, the receiver keeps getting those bytes that are sent, and let 1700 be the sequence number of the last byte that was read by the application at the receiving process. And the receiver has received some more bytes of data continuously in order, and the last byte that was received in order is 2100. So that's why I say the next byte expected at the receiver side is 2101, to indicate that's the next byte to arrive in order to consider the data has arrived in order. Now some data could have arrived out of order, so after 2100 some data has not come, right? The immediate bytes expected have not come, but some subsequent bytes have arrived at the receiver. So in the internet, the packets could take independent paths. So some packets could take a longer path, some could take a relatively shorter path, and so on, because IP provides a best effort service. We cannot guarantee that every packet should take the same path in the intermediate networks. So some bytes could have arrived out of order. So if the bytes have arrived out of order, the receiver is not going to typically acknowledge for those bytes. So it's going to keep sending acknowledgement only for the 2100 byte, that is the last byte that has been received in order. So what it will do is it will keep buffering the bytes that have arrived out of order. So let us indicate the last byte received is 2400. So as you see in this sender side here, the sender has sent up to 2600 bytes. So the receiver has received up to 2400 bytes. That's the last byte received. And among those bytes, up to only 2100 has been received in order so far. Okay, so we need to keep into consideration or keep track of all these parameters at each side. So now what we really want to calculate in this problem is how much more the sender could send. Okay, so for that I also need to give you the receiver buffer size. So what is the total buffer space available at the receiver? So let us assume it is 1500 bytes for this example. Okay, so that means how much more the receiver could advertise as space being available. That's what we need to first calculate. So the receiver has received up to 2400 bytes, even though some bytes are missing in between. When it has received up to 2400 bytes, it means the earlier bytes that are yet to come or at least being sent by the sender, because 2400 is it's a byte that has been sent after the earlier byte. So if this byte has made it to the destination, the other bytes that were sent earlier should be on their way. So the receiver should allocate space for those bytes and prepare as if they are to be received. So it cannot advertise that space as being available. It has to dedicate that space for the bytes that are expected to be received. So this 2400 is the last byte received, and 1700 is the last byte read. So basically this is the difference, last byte received minus last byte read. So that much of buffer space has to be allocated for the bytes that have been already received and the bytes that are expected to be received. So that difference is 2400 minus 1700 is like 700 bytes. So out of the 1500 bytes for the buffer space, this 700 bytes have to be dedicated for the bytes that are already received and are expected to be received. So the remaining 1500 minus 700 is 800 bytes. So that is what the receiver can advertise as the advertised window, as the buffer space available. Okay. So in an acknowledgement packet that is sent for this 2100th byte that was received, that was the last byte to be received in order, the receiver will send an advertised window of 800 bytes. Now the source gets that acknowledgement packet, and from the source point of view, it has sent up to 2600 bytes, and 2000 is the last byte that was acknowledged. So it has to really get acknowledgement for the remaining. As I said, the receiver is not going to acknowledge for every byte. It's going to acknowledge for the last byte that was received in order in a sliding window. So but nevertheless, from the source point of view, this 600 bytes, 2600 minus 2000, is what is called the outstanding bytes, which is the bytes that have been sent but not yet acknowledged. So there's the sender. From the sender's point of view, it has to take this into consideration that these 600 bytes will make it to the destination, and the receiver should have space to accommodate these 600 bytes. So out of the 800 bytes that the receiver really advertises as its available window, from the source point of view, it has sent 600 bytes. So what it can send further is the advertised window of 800 bytes from the receiver's point of view, minus the outstanding bytes, the bytes that have been sent from the source point of view but not yet acknowledged. So minus the 600. So the remaining is 200 bytes. So that's what the source can send furthermore at this point. Okay. So given the numbers like I've shown here along the receiver buffer size, you should be able to do this calculation and give an answer how much more the sender could send. If the sender cannot send anything more, then it is like 0 bytes. That's what it should be able to send. So let us go through one more example that will kind of make it 100% clear, like how in terms of data packets things are sent. So let us say the destination advertises a window of 2500 bytes, that is the amount of bytes it can store. So the source gets that information in the acknowledgement packet set up as part of a TCP connection and starts sending data. So let us again assume every data packet is 1000 bytes of data. So to accommodate 2500 bytes, the source can send 3 packets, so that is the sliding window size. So it sends the first packet 1 to 1000 bytes, and then 1001 to 2000 bytes, and 2001 to 2500 bytes. So these are 3 packets that are sent, and all the 3 make it to the destination, and the destination starts acknowledging for them. So it will acknowledge for the 1000 bytes that have been received. So the sequence number in the acknowledgement field will be 1000, indicating that's the last byte that was received in order. And those 1000 bytes will be still buffered. They won't be read by the application at the destination site right away. So in this first acknowledgement packet, the destination can advertise the window of 2500, that's the initial buffer space that was allocated for the session, minus this 1000 bytes of data that was received in order. So the remaining is 1500 bytes. So that's what the destination can advertise as available advertised window size. So when that acknowledgement comes to the source, it is an acknowledgement for the byte number 1000. That means bytes up to 1000 have been received in order. So the source knows from all this information that the last byte sent and last byte acknowledged. So the last byte sent is 2500 and the last byte acknowledged is 1000. So 1500 bytes is the outstanding bytes, the bytes that have been sent and not yet acknowledged. So it will do 1500, the advertised window, minus the outstanding bytes, which is also 1500. So it is 0 bytes. So that is what is called the effective window size, which is how much more the source could send, which is 0 bytes. So that's why after receiving the first acknowledgement, the source doesn't send any new data, it just keeps quiet. Now meanwhile, the second data packet makes it to the destination, and the destination will now see it as received up to 2000 bytes in order. So again, those bytes are still buffered in the buffer space, they are not yet read by the application. So 2500 minus 2000 is 500 bytes. That's the available window or advertised window, we can call either way, is what is the destination can advertise in the acknowledgement, second acknowledgement packet. Now again, so when the source gets the acknowledgement for the 2000th byte, it will calculate how much more is outstanding. It is sent up to 2500 bytes, so 2000 is the last byte acknowledged, so the outstanding bytes is 500 bytes. And the available window is also 500 bytes. So 500 minus 500 is 0, so it cannot send anything more. So it just keeps quiet again. Now the destination gets the third data packet, which has the last 500 bytes of data that was sent. And so they are again buffered, not yet read by the application. So all the 2500 bytes of buffer space is now full. So the receiver will simply acknowledge advertise window size as 0 bytes available. So when the source sees its available window size at the destination is 0 bytes, it won't even think of sending any new data. It again keeps quiet. Now time passes on like that. After a while, the application, so this axis, this line here is basically the time axis. So as you go from top to bottom, the time progresses. So after some time, the application at the destination site starts reading some bytes from the buffer space. So it reads, say, 2000 bytes of data. So that means out of the 2500 bytes in the buffer space, 2000 bytes have been read. So the available window is now 2000 bytes. So the destination needs to kind of let the source know this information, because the source cannot automatically know this. So what the destination will do is, if it has already advertised as 0 bytes, because of which the source is not sending any more bytes, it will send a dummy acknowledgement packet for the last byte again received in order, which is 2500. So this acknowledgement indicates up to 2500 bytes have been received, and it advertises a window of 2000 bytes because that's what is now the available space. So when the source receives it, it figures out that all the 2500 bytes it has sent have been received and acknowledged, so there's no more outstanding bytes. So it can now send the advertised window of 2000 minus the outstanding bytes, which is 0. So it can send 2000 bytes more of new data. So it sends two data packets, 2501 to 3500 bytes and 3501 to 4500 bytes. Those are the two data packets that are sent. And when the first one makes it to the destination, it will acknowledge for that 1000 bytes. So 3500 is the last byte number that was received in order. So again, out of the 2000 bytes of buffer space, 1000 bytes have arrived. So the advertised window is 1000 in the acknowledgement packet. When the source gets that acknowledgement packet, it figures out that 1000 more bytes are outstanding yet to be acknowledged. So 1000 of bytes of advertised window minus 1000 outstanding bytes means the effective window size is 0. You cannot send any new additional bytes. So the source keeps quiet. So now the destination gets a second data packet up to 4500 bytes of data, and they are buffered, so there's no more available window size. So this destination can advertise 0 bytes as the available window bytes, so the source again will keep quiet. So time goes on like that. The application will read another 1000 bytes of data, clearing 1000 more bytes for the buffer available window. So the destination can send a dummy acknowledgement for the last byte received in order, which is 4500 bytes, and the acknowledgement makes it to the destination source, and the source can now, if it has some more data, it can send and continue the process. So this is how the transport layer protocol running at the source and destination will coordinate and make sure the destination is not getting overflowed with the data sent by the source. So this is called the flow control problem. So basically this is the problem of how the source can adjust its sending rate according to the buffer space, which are the resources available at the destination. Okay, so if you have any question, we can ask using the microphone or type using the chat window. Let me just save this and I'll be back in a second.